talks and we Okay, yeah. Can you hear me? So, I think I'm one of the least likely people you would expect to tell you about the transit of Venus. My sort of day job is as a cosmologist, and so I'm usually interested in questions about the universe as a whole. And so I don't talk very much to people like Peter, who study planets and objects inside the solar system. But another one of my hats, I teach the Intro to Astronomy course at Johns Hopkins. So I actually am familiar with this. And but in particular, the transit of Venus historically is one of the most interesting measurements or observations. There was a time back in the 17th, 18th, even into the 19th century that I would say that the transit of Venus was the most important measurement one could do to understand what was known of the universe at the time. Actually, in many ways, is a cosmological measurement. It is also one of the first, if not the first, large international collaboration made to answer a question, which is very similar to the way we do science today, but would have been very unusual back in the 17th or 18th century. So, just for starters, I assume you've seen pictures of this on the news, what to expect, but this is Venus, of course. It's about 1% the size of the sun. Here's the sun, and this is a photograph taken in 1882. So the reason that the transit of Venus is so interesting, or was so important, has to do with the measurements of distances and answering very basic, simple questions that we had about the universe, what we would call the universe at the time. And I think it's interesting that it's a big question if it can be stated very simply, or could be understood by a 5-year-old. Maybe there's a 5-year-old in the audience here. But questions like, how far away is the sun? Or which is bigger, the Earth or the sun? And once you know which one's bigger, you might even guess which one is going around the other. How far away are the planets? This would not have been obvious to you many hundreds of years ago. How far away are the stars? How fast does light travel? Is it instantaneous, or does it take some amount of time to reach places? And how could you possibly figure out something like that? These are all questions that people had in the past that could be addressed by the transit of Venus. Now today, we have some related questions that, if I get time to mention, actually also in some ways relate to what we can learn about the transit of Venus. Questions like how old or big is the universe, and research that I do, what is dark energy? But addressing these questions come about in relation to the transit of Venus because you need knowledge of the astronomical unit in order to answer these questions. The astronomical unit is the mean separation between the sun and the Earth. And as I'll talk about in a little bit, the transit of Venus is one of the best ways or was one of the best ways in the 17th, 18th, 19th century of determining this number and then addressing all of these questions. So the first effort that I'm aware of to in a sensible way, measure the astronomical unit, the separation between the Earth and the sun, was done by the ancient Greeks. The Greek Aristarchus of Samos had a very clever idea. He reasoned that if you waited until the time when the moon was half lit, you see here, right, one of those days where there's that nice line going right down the center of the moon, one half is dark, one half is light, that at that time it ought to be that there's a right triangle set up, a triangle with 90 degrees on one end between the Earth, the moon, and the sun system. And that he thought if you could measure this angle, the angle as you sighted down the intersection of the moon and the sun, and you knew, and they knew, they had an idea of the distance between the Earth and the moon because they knew approximately the size of the Earth. They knew from the curvature of the Earth, they knew the relative size of the moon to the Earth, which you can tell during lunar eclipses how long it takes the moon to pass through the Earth's shadow. And the angular size of the moon, then you know the distance to the moon. If you could then measure this angle, if Aristarchus could do that, he could then solve this triangle. A little bit of trigonometry that you may remember would give him this length. He measured this angle, so I should say it's almost two right angles. If you can imagine, the sun is very far away compared to the Earth and the Moon. So he measured an angle of 87 degrees, and if you don't remember your cosine, I have a nice little table over here, but that would imply, if this were 87 degrees, that the ratio of this length to this length is about 20, okay? Meaning the astronomical unit would be about 20 times the Earth-Moon distance. Now, Aristarchus did not get this number quite right. You could imagine this would have been a very challenging measurement to make. You have to stare into the sun, okay, and at the same time identify this bisector of the moon, and without instruments and tools, probably getting within a couple of degrees is pretty good. The right answer is 89 degrees 50 arc minutes, and the cosine function is actually quite steep, which means that he was off by about a factor of 20. So he was not exactly right. Nevertheless, even his answer, combined with the angular size of the sun, told Aristarchus that the sun was about 5 times as big as the Earth. Now, the right answer is that the sun is about 100 times as big as the Earth. But this allowed Aristarchus to realize something important that most people did not realize at the time, which is that the Earth goes around the sun, not the sun goes around the Earth. He reasoned that the smaller thing should go around the bigger thing, which is very sensible. Now, people generally did not believe Aristarchus, and so, as you know, the Greeks held on to this idea that everything was revolving around the Earth. Aristarchus was declared impious for even suggesting something otherwise. The Greeks, in fact, thought that the Earth was stationary. They noticed that when you fired an arrow in the sky, it would come straight down. So how could it be that the Earth would be moving around the sun? They didn't understand the concept of inertia, that the motion of the arrow would be the same as the motion of the Earth, so it still would come straight down. Okay, so the next chapter in our story of the astronomical unit and the attempt to determine it comes from Johannes Kepler, very famous astronomer and mathematician. And Kepler made use of the new idea from Copernicus that all the planets went around the sun, and he combined that with another famous astronomer's observations, Tycho Brahe. And from that, he derived 3 empirical laws. And one of those laws, his third law, which he derived or developed in 1618, he didn't derive it, this was just empirical, was that the square of the period of any planet would be proportional to the cube of the semi-major axis, okay? P squared is some constant times r cubed, which means that you can immediately measure the periods of all of the planets. You just wait and see how long it looks like it's going to take for one of the planets to come back to where it started. And then you know the distance to all the other planets, as long as you know the distance to one of the planets. If you could just know the astronomical unit, which is indicated by 1 here, then you would immediately know the actual size of the solar system. You would know the separation of all the planets. So again, this is a very important observation that you could make to determine the astronomical unit. And once Newton came along with his laws, which actually explain what this constant was, turns out it involves the mass of the sun. If you know the astronomical unit, you can actually determine the mass of the sun. So again, so much was riding on being able to measure the astronomical unit. Another example comes from determining the distance to the stars by a technique known as parallax. Parallax is just a fancy word for triangulation, which is a fancy word just for making triangles again. And so here is the Earth, and on its journey around the sun, if you were to look at a nearby star relative to distant stars, you would see this star appear to move back and forth every 6 months. It would move through an angle known as the parallax angle. This is the same phenomenon if you hold your arm straight out and you put your thumb up and you open one eye and close the other and then switch back and forth, you generate the same effect by moving the position of the viewing. Yes, you can try this demonstration at home, or here if you want to look silly. So because of the 5 centimeter separation between your eyes, you will see your thumb move back and forth by about 3 degrees if your arm is about a meter in length. In fact, you can use this to measure the length of your arm if you're so inclined. So one can determine the distance to the stars by measuring this angle by which the stars move, if you know, again, the astronomical unit. There's the separation between the distance of your two eyes in this case. Now, the Greeks could not see this effect. They could not see the stars moving back and forth. They could not see any parallax. So they reasoned, again, incorrectly, that the Earth was stationary, that it was not moving around the sun. They just could not fathom that the stars were so far away that this parallax angle is minuscule, that it is of order 1 second of arc, 3,600th of a degree. So generally, it was just something that their technology, and without telescopes, that they could actually measure. It was not actually first measured until about 1838 by Friedrich Bessel, who measured the first parallax to a star of about a third of an arc second to the system 61 Cygni. But again, without knowledge of the astronomical unit, you would not know the distance to the stars. And then finally, the last example comes from Ole Romer, an astronomer, Danish astronomer in the 1600s, who developed an ingenious way to determine how fast light traveled. And up to that point, it was a great debate whether light was instantaneous, whether you just, for example, opened your eyes and the light came from your eyes, or whether it was just could travel infinitely fast. And Ole Romer realized that as he observed a particular phenomenon, which was that the moon of Jupiter, named Io, would travel around Jupiter, and about every 42 and a half hours it would make a trip around. And so one could identify a specific moment when Io first goes behind Jupiter, sort of like the transit in reverse, where the object that's orbiting is going behind instead of in front. And as the Earth moves away from Jupiter, as you see here, it would take longer and longer for Io to appear to go behind Jupiter. And he realized that's because of this growing delay, the fact that light has to travel further and further. And finally, when the Earth goes from being on one side of its orbit, right close to Jupiter, to the other side of its orbit, that is when the light had to travel the full diameter of Earth's orbit, which is twice the astronomical unit, that delay built up to about 16 and a half minutes. Okay? So again, once you know the astronomical unit, you would immediately know the speed of light. Okay? So again, a very profound, very important observation depending on knowledge of this number. So, on to the transit of Venus. So it was Kepler and the British astronomer Jeremiah Horrocks who in the 1600s first realized that this event even occurs. There's a little bit of a tilt between the orbits of Venus and the Earth, so it doesn't happen very often. The lineup actually occurs only about twice every 130 years. It's actually Horrocks who realized that it would actually happen a second time in the beginning of the 17th century. But it was Edmund Halley, the famous astronomer for whom the comet is named, who in the late 1600s realized that during a transit of Venus would be the greatest opportunity to well measure this astronomical unit. And his idea, which is sort of shown here, is that two observers, one would go to the north, to a northern latitude, and one to a southern latitude. Now, from the northern latitude, the observer watching the transit of Venus would see the transit projected along this sort of southern limb of the sun. The southern observer would see the transit of Venus projected along a northern limb. That is, Venus would travel along a different path along the sun depending on where you were situated on the Earth. And he thought the best measurement they could make would be to measure how long it took Venus to transit across the sun. Now, when Venus is projected along the sun on a longer chord, it will take longer, and by some simple geometry, I'll leave this as an exercise for the audience to solve for the difference in time, which tells you the angle between the two observers. So the two observers measure this time difference, they determine this angle, and then they measure their separation, right? Again, there are different latitudes, we know the size of the sun, and so you can solve this triangle and determine the astronomical unit. The only problem is that this happens, as I said, only about twice in 130 years. When Halley realized this was the important observation to make, it was the 1680s, and the next transit wouldn't be until the 1760s. So he would not live to see this, but he encouraged an international collaboration to fan out across the Earth and make this observation. After all, the weather could be cloudy, as we are currently seeing. So it's important to send observers in a number of different locations. If you were having trouble understanding or seeing the geometry of that, here's a little animation of what it looks like. But here on the Earth, from the perspective of the northern observer going through Venus, seeing the shadow of Venus at this southern part of the sun, and then the southern observer seeing the transit of Venus on the northern part, and how measuring the transit time would tell you what the angle was between these observers. Okay, so the history of the actual observations. Horrocks, as I said, was important to realizing there would be a second transit in this pair of 130 years, and was the first to actually observe the transit of Venus in 1639. It was just observed at the 1 latitude, so there was no ability to measure the astronomical unit from this. But Halley encouraged observers to observe the 1761 and 1769 transits. And so, as I said, observers went all over the globe to observe this. Some very famous explorers got involved in this. Captain Cook took astronomers to the island of Tahiti, where they made the observations. Mason and Dixon, who are famous for marking the border between Maryland and Pennsylvania, the famous Mason-Dixon line, actually went to the Cape of Good Hope. There are all kinds of interesting, tragic stories of people trying to make this measurement and struggling. A French astronomer, Lejeune just kept struggling. He lost his wife, he lost his possessions, he was declared dead during the course of 8 years of trying to make this observation. Shipwrecks, all kinds of trouble. There was the 7 Years' War between the French and the English, but they allowed the astronomers to go through the lines and wherever they needed to go. So that's why I say this was sort of the first international collaboration that I'm aware of in science. So the answer they derived was 153 million kilometers, which is pretty close to the right answer of 149.6 million kilometers. Now, our own Professor Simon Newcomb of Johns Hopkins University in the 1880s made the best measurement from observations of the transit in 1874 and 1882. Here's his picture of the transit. So the answer he got was 149.59 million kilometers, so very accurate. Although at some point, by the early 20th century, measuring the astronomical unit by the transit of Venus was surpassed by the use of radar to bounce a signal off of planets or the sun, or spacecraft telemetry, which also can be used to very accurately determine the location of spacecraft, and using Kepler's law, determining the astronomical unit. So the transit of Venus is now defunct as for this particular use. But nevertheless, it's a very interesting observation, and as Peter is now going to talk about, it may not be have as much cosmological use, but it has a lot of interest in terms of the way we come to understand planets that orbit other stars. So with that, I'll transfer to Peter.